Welcome back to Chapter 2. Today we're going to be looking at Section 2, which is on differentiability. Now, differentiability just is the ability for a derivative to be taken. Does it meet the requirements to have a derivative at that point? And so that's what we're going to be looking at today. Our learning targets: use right-hand and left-handed derivatives to show functions are not differentiable at given points. Determine whether a function is continuous or differentiable when given a graph of a function. Determine whether functions have corners, cusps, vertical tangents, or discontinuities. And find numerical derivatives of functions at indicated points. Then use numerical derivatives to graph derivatives of functions. Now, these last two, we're going to be using a calculator to do those, and I'm going to show you that in the meat. So, how f prime of a might fail to exist, how a derivative at a given point might not exist. There are four main ways this could happen. The first of which, we have a corner. Right there, we have a corner. A corner is where the derivative from the left and the derivative from the right are not approaching the same number. So there's that sharp angle. So one of the things of a derivative is if we can take it, that means that it is locally linear. It means if we zoom in on it, it will eventually start looking like a line. If we zoom in on the origin here, it will always be a corner because there's that sharp thing. So it's not smooth. It's not locally linear. So a corner is one place where it might fail to exist. We get corners most of the time with absolute values. A cusp. A cusp is where the derivative is approaching negative infinity from one side and positive infinity from the other side. So that's what this is. So it's like a corner, but it's like a super extreme corner. And again, if we zoom in on this, it's going to look exactly the same. Notice other places, if we zoomed in, say, on this little chunk, it's going to look kind of like a line. The closer we get, the more like a line it will look. However, that cusp in the middle will always be a cusp because one of the derivatives is approaching negative infinity, the other one's approaching positive infinity, and so they're not the same. They have to be the same from each side. The next one, this one's like, wait, it's a derivative, it's smooth. It is smooth, but at the origin here, it goes vertical. So we have a vertical slope there for a second. And so that means the derivative there does not exist. It gets to infinity and then it kind of gets away from infinity. If we were to graph the derivative of this, it would look like this, and we'd have that vertical asymptote right in the middle. Now that doesn't mean that every function like this would have that. I mean, it could be, it didn't have to go fully vertical. So just because it has that general shape does not mean that it will have a vertical asymptote. You have to actually look at what the slope is. And the last one, discontinuity. The derivatives are the same going both places. It looks like, I mean, the slope is 0 everywhere. However, if we were to find the limit coming from the left, we would have the limit as x goes to a, we'll use this one, of f of 0, which would be x. So we'll have f of, we'll go as x goes to 0. F of 0 minus f of x, that should be a, oh well, over 0 minus x. Well, f of 0 is 1, right? Because it's up there. Minus, this one's going to end up being a negative 1 eventually when we get really close. And we get negative 2 over infinity, which, that minus, yeah, because 0 is minus 0. Or negative 2 over 0, so we get an infinite deal because these are not the same. So it has to be continuous. So just like it being differentiable implies that it's smooth or locally linear, it being differentiable also implies that it's continuous at that point. So if it's differentiable over an interval, that means that it's both smooth and continuous over that interval. If it's differentiable just in its entirety, that means it's smooth and continuous in its entirety. So knowing that something is differentiable tells us more about the function. And the other thing we're looking at is the intermediate value theorem for derivatives. So we know the intermediate value theorem. If it goes from a to b, then the function goes from f of a to f of b. You're going to hit every number in between. That's basically it. The one for derivatives, if we have a and b are 2 points on an interval, which f is differentiable, so nothing strange is happening, no cusps, nothing like that, then f prime takes on every value between f prime of a and f prime of b. So if we have a graph with a function, let's just say it's this function, we have a, we have b. So a is going to be a slope kind of like that, b is going to be a slope kind of like that. So throughout the middle part, it's going to hit all those other slopes. Now, that doesn't mean that it can't do other things. For instance, if our a is here and b is here, so we have a is positive, b is negative, means somewhere in between there, it's going to be 0, which gives us a maximum or minimum. We'll see that here pretty quick. But that was illustrating something, but not what I was looking for. So now we have a and we have b. So a is going to be here, b is going to be here. So they're fairly similar. Well, they're both positive. In the middle, we have slopes that are negative, we have slopes that are 0. It doesn't say that you can't have other things, just like the intermediate value theorem. What it says and what it doesn't say, both good things to know. It doesn't say that you can't have other things, but what it says is that from this slope of 1 to this slope of 2, we're going to hit everything in between, which we do. We just also hit a lot of other stuff. We hit negatives, we hit all sorts of stuff. So, just like with the regular one, knowing what it doesn't say is just as important as knowing what it does say. And also like the other one, this is one of the more important things, because we can find those zeros, we can find those maximums and minimums. So that is this section in a nutshell. Again, I will we'll see how to find the numerical derivatives and how to graph numerical derivatives on our calculators during class, and I'll see you then. Until then, keep working problems, keep asking questions, and as always, happy mathing.